Okay, starting in C3 chapter 11, volumes of revolution. To explain what they are and how we do it, we'll just kick off with an example. Okay? So, if we consider this curve, y equals x squared plus 4, what does it look like? Where does it go? What shape is it? What are its key things? It's a
parabola.
Parabola, happy parabola. Yep.
Cuts the axis at 4.
Yep.
Y-axis at 4.
Okay, so it will look like that. Okay. Now, if you've got that, and if the question told you to do this, if it said rotate, now it says here the shaded area, so I better show you a shaded area in a minute. Rotate the shaded area. And what I'm doing here, I'm going to put two more lines on this graph. I'm going to put a line here, and that line's x equals 3, and a line here, and that line's x equals minus 3. Oops. So if we rotate the shaded area around the x-axis for one full turn, what would you get if you rotated that? What would you get?
Same thing like underneath it, something?
That's if you reflected it. If you're rotating it completely, you're going to end up with a 3D thing. If you imagine it sort of rotating and where its path will go, what sort of shape will it be? Will it make? So you're rotating.
Like two big circles, and then
Two big circles at either end. Yeah?
and then it goes like,
And it sort of goes
yeah.
like that. It will give you a 3D shape like that. Yeah, okay. Where your x-axis effectively sort of going through there like that. Okay, a bit like an egg timer on its side type thing. Okay? You're happy that you can visualise that's what you would get if you rotated that shaded area. So this thing here we're going to refer to as it's a volume, it's a 3D thing of revolution. It was generated by revolving a graph around an axis to make a 3D thing. So we get here a solid 3D shape. And this chapter is all about these shapes and, fairly unsurprisingly I guess, calculating their volumes. Okay? How would you find the shaded area here?
Integration?
Yeah, you integrate the area under the curve to find the area of the curve. So what we're going to do here is something similar. Integrating is actually giving you the area of very, very thin strips, infinitesimally thin, and then we sort of add them all up. So what we're going to do here is we're going to imagine one of these strips, and we're going to rotate one of these very, very thin, sort of infinitesimally thin strips around the x-axis. If you imagine that little strip there, it's sort of so narrow that the top of it is effectively flat because it's not over a wide bit of the curve. What would we end up with? What would that give you if you just rotated that strip around the x-axis? Circle, yeah, it's very narrow sort of circle, like a disc effectively, like a very thin cylinder. And what we will do, we'll work out the volume of one of these, and then we'll imagine there are a whole load of them, an infinite number of infinitely thinner ones of them, and we will add those up. That is the process that we are going through. Okay? So I'm just going to try and reproduce that drawing, and I suggest you did on a slightly sort of bigger scale, so we can sort of do some annotations and things. So we have an axes, we have our curve. Okay, that was 4, that was at minus 3, that was at 3. We've got our equation. And what we are going to look at now is this very thin strip. What is its height? What is the height of the strip? You really haven't got to say very much to tell me the answer. X squared plus 4. That is the height of that strip. What is x squared plus 4 equal to? Literally reading off there. What is x squared plus 4 equal to? Y. Okay, yeah, the height of the strip is y. And in this case, yes, it is x squared plus 4. Okay, so it's always going to be y, pretty much. Okay, and in this case, yes, here, y is equal to x squared plus 4. Okay, so the height is going to be y. Then, if we look at the width of the strip, the width of the strip is a little bit of x. And the little bit, I don't know if you ever came across in doing calculus in year 12, a little bit of x. And what's going to happen here, as that gets narrower and narrower and narrower, that's effectively going to become be replaced with the dx in the calculus thing. And when that strip is rotated around the x-axis, okay, so when the strip is rotated around the x-axis, what we will end up with is a very thin disc, if you like, or a cylinder, a little, very thin disc. Or a cylinder, if you want to think of it like that. Now, if you thought of it as a cylinder, what is the volume of a cylinder?
Surface area by...
Volume of a cylinder. Yes, okay, if that's the way you learnt it, yeah, okay, fair enough, you're correct in what you said. What is then the surface area of the circle? Area of a circle?
R squared.
Pi r squared. And then you times it by the height, effectively, of the cylinder, how far the cylinder goes back. Okay? So here, r is going to be that, unsurprisingly. And the height is this little, it's going to be very thin here, it's going to be that distance there. Now, in terms of the top drawing, the r over here, what is the r in terms of what we have got here?
Y.
Yeah, the r is y, which is how high it went up, its height. Okay? And the h, what is h going to be in terms of this then?
Dx or...
Yeah, okay. It will eventually be the dx. It's the delta x which goes to be the dx. So, what will the volume be if I now rewrite this volume formula over here in terms of what is over here? How can I rewrite that?
Pi y squared dx.
Yep, that's right. Okay. So, if you follow that bit, we're coming on now sort of to the red box rule, the main thing, if you like, that if we are rotating, so this is like going to be our sort of red box rule, if you like, here. If we rotate around the x-axis, the volume is equal to. Now what are we going to do with this pi y squared? We're going to add up lots of these little ones, and that's where the integrating comes in. So we are integrating pi y squared dx between two limits. So that's the general sort of red box rule, if you like, for rotating around the x-axis. Key thing is that if you're rotating around the x-axis, there has to be a dx there, and then these numbers here, the a and the b, they are also x numbers. They have to be numbers on the x-axis. So, for the shape that we were going to get for our original question that we were dealing with, so going back to our original question, where we had this shape that looked something like that. That's terrible, supposed to be equal heights either end. Appalling drawing. Okay, I'm just making worse and worse, I think, trying to correct it. What will we do? What calculation and what thing will we do to work out the volume of our specific thing? I will be integrating between. What are my a and b's, do you think, just looking at what we had?
3 minus 3.
Yeah, okay, that's right. Okay. Then it's going to be pi. And what was y actually equal to in this question? X squared?
Plus 4.
Plus 4. Pi y squared dx. Okay. So we do that integration, we will find out the volume of this shape. So if you were doing that integration, how would you proceed from there? You know what my first step's going to be. Move the pi, yeah. Okay. I will first of all take the pi, shift it through. So put my limits in. X squared plus 4 all squared. What should we do with that? Can you?
Square plus 4 cubed over 3.
We haven't got a rule yet that lets you do a function to a power like that unless there's a derivative of it over here. So we have a red box rule for integrating a function to a power, but then we had to have its derivative at the front, which we haven't got. So we can't just do the integration straight. Multiply it out, yeah. And whichever way you want to do that, if you want to do it the grid method for multiplying it out, whatever. Okay, that's fine. X squared times x squared, x to the power of 4, x squared times by plus 4 4x squared, same down there, and over there 16. So, multiply that out, we will get x to the power of 4 plus 8x squared plus 16 dx. Keep the pi outside. Anybody like to do that integration? One of you two at the front?
X to the 5 over 5.
Yeah.
Add x cubed over 3.
Yeah.
Add 16x.
Yeah, that's right. Okay. Normal, straightforward integration. Between your limits, do we all know what 3 to the power of 5 is? 3, 9, 27, 81, 81 times by 3.
243.
243, yep. So when we put the 3 in, the 3 cubed we said was 27, that's not a point, that's a multiplying dot there. So we put the 3 in, we'll put the minus 3 in. What's minus 3 to the power of 5? Yeah, Yeah, because we're doing a minus, and they're all going to be minus power, so they are going to be minus values over here. And don't forget that you still have to times all of that by pi. But don't actually times it by pi in your calculator. Work out this as a number and then just write down it's times by pi. So it's a case of putting that in a calculator. But some of you, if you've got graphics calculators, can just type this in your calculator at this stage, can't you? And get the answer out. If any of you got graphics calculators. And you do that. You can just type that into your graphics calculator and the answer will just come out. Okay? Because it's numeric integration. So, play around with that. Check you can press all the right buttons on your calculator. And we should get an answer. And for those of you looking at the video, the answer you should get is this. And then we're timesing it by pi, so we'll put that in, and it's a volume, so it's going to be units cubed. And then that's the end of that example. So if we know how to rotate around the x-axis, what else might we be asked to do?
Rotate around the y.
Rotate around the y, yeah, so let's have a rule for that one then. So if we rotate around the y-axis to get a volume, just tell me what it's going to be. Come on, just tell me, what's it going to be?
The integral between b of pi x squared dy.
Yeah, that's right. Okay, just swap your x's and y's over. Okay, and that will be what we do for rotating it around the y-axis. Again, rotating around the y-axis, it's a dy there, and these numbers here, the a and the b, they will be numbers on the y-axis. I do recommend you do a drawing for these questions. I think it really does show you what's going on. So we'll do another example now, and this will be around the y-axis one. So we will find the volume generated by rotating the curve y equals x minus x squared so I said we're going to do one around the y-axis. This is another around the x-axis one. A bit disappointing, really. Find the volume generated by rotating it around the x-axis. There is a around the y-axis one coming soon. We will use the area bounded by curve x-axis. I promise there's a y-axis one coming. Move that up. So the first thing to do is to sketch the curve. So if we are going to sketch this curve, what does it look like? Anything we could do sensibly to help us sketch it?
Make a table.
Could make a table. Hoping Joe's going to give us some other insight into this curve. What could we do to? Could we rewrite it in any way? Okay. Factorising is a good thing to try, yeah. If you try to factorise it, what will we get if we factorise it?
1x, 1 minus x.
Yep. So if we can write it like that, what do we now know about it if I was going to sketch it?
Minus 1. Is minus 1 the root?
It's what makes these things 0. What makes that 0, x equals 0. So it's got a root there. What makes that 0, x equals
1.
1, yeah. Okay. So it's going to go through there, and it's going to go through there. It's a quadratic. Happy or sad?
Uh,
Sad, because it's got a minus in front of the x squared. So that's going to be that. And we had to find the area bounded by the curve and the x-axis. Well, there's the curve and the x-axis. So we're just talking about that area there. And we are rotating this one around the x-axis. So we are rotating that one around the x-axis. You just want to do that to help yourself. So, the rule we had for finding the volume when we rotate around the x-axis was integrating between our limits a and b, pi y squared dx. I'm going to shunt the question off the top, keep this here. My a and my b will be these points here, so it'll be 0 and 1. Take my pi through the integral sign. Y squared is the x minus x squared squared. What did we do last time with a bracket squared?
Expand.
Yeah, so do that any way you like. That's right. Nothing new from here now. It's sort of standard year 12 integration really from here. So I'll leave you to finish that one off. If you can, find a calculator somewhere. Okay? Or you can do it without a calculator, because you're going to give your answer in terms of pi. So you should be able to do this, particularly since you're substituting just 0 and 1 in, without a calculator anyway. Oh, very silly of me there, I didn't actually do the integrating bit. Brain dead. Try it again. For anyone watching and thinking I'm particularly thick, it's the last day of a very long half term. So we really have got now rotating around the y-axis example. We're going to start with the curve y equals log of x, ln x, bounded by the y-axis and two lines y equals 2 and y equals 5. So the first thing to do would be to do a sketch. What does the graph of y equals log of x look like? Where does it go through? One of these you should know.
Goes through 1.
On which axis?
Y-axis.
That's the graph
No,
of e to, that's the graph of e to the x. E to the x goes through 1 on the y-axis. E to the x is that one. This is log x, which is its inverse function. Does, yep, okay. It goes through like this and gets sort of flatter and flatter and flatter as we go. So that is 1. Then I'm interested in the lines. I'm not so shallow now, I've made it a bit difficult for myself, but the lines y equals 2 and y equals 5. So the area bounded by the two red lines and the y-axis and the curve will be this here. So that is the area I'm dealing with, and I'm rotating this one around the y-axis. So the rule we had for rotating around the y-axis for the volume was between our limits pi x squared dy what's x squared? That's our issue here. What does x squared equal? We've got y equals log of x. What am I going to have to do to that to find out what x is and then x squared is?
E.
Yeah, e to both sides effectively. So e to the y, e to the log of x. The whole point of this is e to the log of x is just x. So this is what x equals. So x squared, what will x squared be?
E to the y plus 2.
Think carefully. It's e to the y squared.
So let's say it's the 2y.
Yeah, times the power, so if you're doing a power to a power, e to the 2y. So the integral that's top right for this one will become, well, my two limits are going to be the 2 and the 5. The pi I will take outside of the integral sign, and I'm integrating x squared, which is e to the 2y dy. So what do you get if you integrate e to the 2y? Yeah, e to the 2y, because we're integrating, it's an over 2. I'm integrating between 5 and 2. Because this 2 here is just a number, you could take that through the bracket if you want. So if you wanted to, you could move that 2 and just deal with that. Okay, you can just take the 2 there through, just like you can take it through an integral sign. You can take it through there as well. So, substituting in, I've got my pi over 2, put a 5 in there, I'm going to get e to the 10, put a 2 in there, I'm going to get e to the 4, and that is my answer in units cubed. That's an exact answer. If they wanted you to give it to 3 significant figures or something, I've got down here that it's about 34,500. It shouldn't be there. Units cubed. So I do have some more examples, but I think we might just stop at that point and just have a go at practicing some ourselves from the book.